We have one more key concept before we conclude this particular module and send you off into doing a whole lot of exercises. So here in example 2.5, what we're going to do is extend these ideas of conditional probability and in essence really derive a couple of different variations on what's called Bayes' theorem, which is really all about turning conditional probabilities around to get at what we want, starting at a place that maybe we don't have quite what we want. And what I mean by that is the following. Let's go back here a little bit and remember that when we talked about joint probabilities, two things happening simultaneously, one way that we could look at this was the probability of one event occurring conditioning on the other one having happened and then weighting it by how that other one happened, right? This is not an independence argument. We haven't gone to that step here. We don't assume independence at this stage, right? If it happens, then it simplifies what we have here. But right now, that's the conditional probability, and then we weight or multiply by the marginal or the conditioning event, right? That's one way we could have written it. Now, if we have the other information around, we have B given A information, then we could have also written this joint in this fashion. And this is how we can then work with then the information to turn things around, right? So presuming that we actually knew B given A, but what we wanted was probability of A given B, then we can use this key cornerstone up here, the joint, and how this works out, then to effectively rewrite this as the following, right? So we just set these two equal and solve for the one that was of particular interest, right? And note that we could make this even look bigger or more comprehensive when we went through and said, well, all right, we know probability of B given A, and that could actually be broken out, right, as probability of B, this one down here, now the marginal of B, because maybe we don't know that. Well, if we know B given A, then we can weight that by A, and then by total probability theorem, then we can also look at probability of B given A prime times the probability of A prime. Right? And remember here that A prime is the complement of A, that in the Venn diagram, that universal set, that's all, right? We break this up into, there's our event A, and everything else then is A prime. Right? Now B and B prime also occupy this space, but in different weights. Right? And I don't want to confuse it by showing that Venn diagram sitting on top of that one. Right? So, and you'll oftentimes see Bayes' theorem written this way, where we got this information. In the context where this oftentimes happens, for instance, is where we're looking at a piece of equipment that's doing some measuring, and we want to go through and calibrate it. So we have, before we do the calibration, we think that here's the likelihood of certain outcomes and certain accuracies. Then we go do the calibration exercise, and now we have what we call posterior probabilities. So prior and posterior probabilities are where this comes into play. And we'll see this come back to us later on, and oftentimes I don't like to really introduce Bayes' theorem formally until we get to that specific application, because good golly, this just looks like a bunch of babble, right? And probabababble is actually sometimes an accurate phrase for what probability sounds like to the uninitiated or to those struggling to first encounter this, and sometimes even to those that have seen it a lot, it just sounds like a bunch of babble, right? So don't worry too much if this seems a little bit confusing. It makes a lot more sense when you get into a specific problem, a numerical problem where you really have to apply these kinds of ideas and concepts. So I encourage you to take a look at the introduction in Montgomery and Runger, but as we move along, we'll see this come back to us, and when we get into some specific context here, it'll make a lot more sense if you've not already encountered Bayes' theorem.